Tonight's first video is all about forces. By the end of this week, I want you to start seeing the world in terms of forces, not just objects. So it's where you might see this polar bear here. I see some forces. I see the polar bear's weight, or gravity, pulling down on the polar bear. And I see a normal force pushing up on the polar bear. Talk more about what those means, but just an idea of how physicists see the world. Here you might see this tiger. I see some other forces. I see gravity pulling down on this tiger. Assuming he's floating, I see a buoyant force on this tiger. So it's gravity, a buoyant force. I see that maybe the water might be pushing back on the tiger with a type of friction as the tiger tries to push through the water. Here with this person falling, I see gravity pulling them down. I see air resistance trying to push them back up. By the end of this week, the world will become a set of forces to you. So let's go over the basics of force. If you ask yourself what causes things to start or stop moving, the answer is force. And these are the basics. You should know these backwards and forward before stopping this video. So you should know everything on this slide by the time this video is done. A force is a push or a pull on an object. Anything that pushes or pulls, that is a force. Forces are vectors, so they always have a magnitude and a direction. I won't just say 5 newtons, I would have to say 5 newtons to the right. And the unit of force is newtons. 1 newton is 1 kilogram meter per second squared. And that's where that unit that I talked about before comes from. So if you work this backwards from force equals mass times gravity, newtons equal 1 kilogram meter per second squared equals a kilogram times an acceleration, meters per second squared. And as I told you when working with weight problems, this gets easier to write kilograms times newtons per kilogram, because then you clearly work out to newtons. And it works out here too, because you go kilograms times meters per second squared is kilogram meters per second squared is a newton. Now I went through that really fast. It'll become more familiar to you over the week. Finally, velocity and acceleration are not forces, and a lot of people confuse this. Whenever they see a velocity vector, so if I say there's a velocity that way, many people will want to say, oh, well, there's a force from that velocity. And that is not true. A velocity is not a force, and acceleration is not a force. Forces are their own separate things. Those are the main points for tonight. Now what I'd like to do is really quickly go through all the types of forces we'll use in this class, and this will be really fast. I gave you a guided notes page. You should follow along on that. So if you need to pause and find that notes page I gave you today, do so now. Alright, gravity is the attraction to a massive object. Anything that has mass has and can experience a pull of gravity. So if a thing near the Earth has mass, the Earth's gravity will pull on that thing with a force we call weight, Fg. The force of gravity is always toward the center of the Earth, so whatever you are, it's toward the center. Every mass has gravity, and even you. You just don't feel your gravity or other people's gravity because we're not that massive compared to things like the Earth. Finally, scientists still do not really understand the reason for gravity. There are some ideas, but not any super clear ones. Next up, the normal force. Now, gravity and the normal force will be the most common forces we talk about in this class. Anytime there's gravity pulling something down, if that thing is not falling, there must be some force to counteract gravity. So if we got the forces of gravity here, the reason that object does not not fall is because there is a force pushing back up, and that's called the normal force. This is like a support force. So if a book sits on the table, there's a force of gravity pulling the book down and a normal force pushing back up. Also, the normal force is always perpendicular to the surface, so it always forms a right angle. Notice here, the normal force is straight up forming a right angle. But here, in this second example, since our table is now slanted at some angle, so the table is now slanted at some angle, the normal force still has to be perpendicular to the table. So the normal force has to slant too. Friction. Whenever you have a velocity, in most situations, there will be a friction the other way. And the bigger the velocity, the bigger the friction, the more rough the surface, the bigger the friction. So, friction is always parallel to the surface you sit on, which you see here. We've got ice, and we've got concrete, oddly spelled because of the computer. But on the ice, whenever there's a velocity to the right, there is a friction pushing back to the left, so the thing is sliding to the right. Friction's trying to push it back. On the other example, the thing on concrete, there's a velocity to the right. Friction tries to push it back. So friction always opposes motion, always opposite the velocity. And we will sometimes ignore friction when solving problems, but that will be clear in the problems. It'll either say a smooth surface or no friction, or a rough surface or with friction. So smooth means no friction, rough means with friction. Tension. Now this is not tension like you feel between your friends when something's awkward. Tension is whenever there is a rope or cable or a wire, something holding up an object. There's always gravity on Earth, and so if something is being held up by a wire, there has to be a force counteracting gravity, and that is tension. So we've got gravity and tension. Tension can also act at angles, so if we've got gravity pointing straight down on this book on the right, there can be two tension forces that counteract gravity. Every string gets one tension in a problem. So a string can't have multiple tensions. There can't be a certain tension here and a certain tension here in this string. The tension is the same throughout any string. There are spring forces. So whenever you compress a spring, which means squish it, or if you stretch a spring, which means pull it out, the spring wants to go back the way it was. So in this example, we have a hand that's pushing the spring in, and then the spring is pushing back out. So that would be the spring force, the thing trying to get the spring back to the way it started. So the spring always wants to return to the way it started. Air resistance. Air resistance is the friction of air. That's the best way to think about it. Whenever something is flying through the air, there is always an air resistance to oppose it. So here we've got this plane, and it has a velocity to the left. So that's the velocity of the plane. Remember, velocity is not a force, so that's not a force. But then we have air resistance pushing back, opposing the velocity. So just like friction opposes motion, so does air resistance. And again, we will often ignore this when problem solving, but if you're ever shown an airplane, and the problem says draw a free body diagram, which is in the next video, you must include air resistance. So anything flying through the air has air resistance. And even things on the ground, when they're moving, have air resistance. So if we have a velocity of a box on the ground going to the right, so the black arrow is its velocity, there's going to be an air resistance opposing its motion. Now, we usually just include that all in friction or ignore it. But, just so you know, things moving on Earth, where there's air, experience air resistance. Buoyancy. Whenever you have something sitting on water, like this boat here, there is a force of gravity trying to pull it down. And instead of a normal force of water, we call it the buoyancy force. Okay? And it's the support force from water, so like a normal force specific to water. It's always perpendicular to the surface of the water, so forms a right angle. And the more water that the object pushes out of the way, so that boat obviously sinks a little and pushes some water out of the way, the more buoyant force is pushed back up. So you could think of that as like bigger things get more buoyant force. Thrust. Thrust is the force that comes from engines when the engine throws things out of them. So notice back here you've got fire coming out of the engine, and that fire provides the force of thrust that pushes the rocket up. And I spelled that out because we had force tension was Ft. And things like rockets, planes, and jets use thrust. Lift. Lift is the thing that forces a plane upward. And it's generated by the shape of the plane's wing. This is explained by what's something called Bernoulli's principle, which we'll get to later. But basically, gravity wants to pull the airplane down, but there's a force of lift generated by the air moving past the wing that pushes the plane up, and it forces the plane upward. So there's a lift force on a plane flying through the air. In general, there are two categories of forces. Contact forces, like friction, tension, normal force, spring, air resistance, thrust, lift, and buoyancy. These are all forces that require touching. So things have to be touching in order for these forces to happen. However, there are other forces called action at a distance forces, like gravity, the magnetic force, and the electric force. These two we'll study later. But these do not require touching. All right, that's the general rundown of forces. Sorry it was long, but I had a lot to cover. Make sure you can at least name all the forces in this video by tomorrow. So they're all listed here. Look back through which ones can you name. If there's some you can't name or aren't sure about, maybe scroll back in the video to where those were. That's all.